Thank you. Hello, everybody. It's a real pleasure to be here today, and I will present in the work that I have done with Ramya Deshpande, Michael Brenner, and Alma. No? Okay. That has to be very close. Yeah. All right. So it's a pleasure to be here. I will present in this work that I've done with Ramya, Michael, and Alma. And I will proceed to explain the two let's say the two halves of the title of my talk. And but before I will take a brief detour, and as I have had like many interesting conversations in these days with people that kind of share the same goal in this conference, the question, the overarching question that this talk is trying to find an answer to in a very specific setting is, of course, can we learn local interaction rules that produce desired emergent properties in systems? And of course, we would like to argue that quantitative understanding is always better than just a qualitative one for a number of reasons. So asking the question how much, actually more than asking how and what, is important not only in science itself. Of course, many discoveries are driven by precise measurements of things, but especially in engineering. In fact, if you know how to build a bridge in principle, but you don't know how big you should build it, then there's not a very useful bridge and probably a very dangerous one. So how do you, let's say, it turns out that inference, this is something that you want to do in science, fitting parameters, and engineering kind of share the same structure, let's say, which is the fact that you want to have a target function or data distribution, and you want to find the parameters that either best explain that data distribution or the parameters that will generate your desired outcome. And in the last years, let's say, people have come up, so the way in which you could do this, one of the ways, of course, is to define a cost function that defines how far away you are from your desired outcome or your data, and try to minimize this cost function. And a very efficient way of doing these kind of things that has been used successfully in the past, let's say, most successfully in the past 10, 15 years, I would say, is stochastic gradient descent, of course. And the problem with stochastic gradient descent is that you need a gradient somewhere to use it. And this is where differentiable programming actually comes into place, because if you want a gradient and you have an arbitrary complex simulation, you have to differentiate throughout the simulation, which is something you could in principle do by hand if you really wanted to, but this is usually not feasible. And so I will try to show you how we are trying to apply this principle to a specific problem, that is morphogenesis in this case. So there are a lot of models that people have come up with to describe morphogenesis. Of course, countless, let's say, physical models of real biology. Some people have been trying to, at least this is the ones I know of, there's probably many more, have been trying to do this also in the artificial life community, to try to come up with emergent symmetry breaking structure, bilateral symmetries and all these kind of things, reconstructing some shapes. And of course, a limitation of this is that, well, there are like two different kinds of limitations. The first is that many of these models, the ones that are discrete, are not really differentiable. So you need to resort to evolutionary algorithms to fit them. And the other one is actually more of a problem in the sense of a model itself. This whole procedure is just as good as the model that you choose to describe your real life system. If your model of the bridge is not very precise, then the predictions that you will make about how big the pylon should be will not be very precise and pretty much useless. So if we want to move closer to biological description, we have to factor in some additional, let's say, constraints in the systems, namely, and most prominently, the adhesion between cells, the fact that cells grow and they have excluded volume interaction, meaning that they push onto each other. They are not really fixed on a grid. And there's diffusion of chemicals. And so the only example I know of, at least, of a system that is trying to model some of, not of these things, but let's say the morphogenetic process in principle and is differentiable, is the neurocellular automata, which is not actually dealing with discrete decisions. So you can actually backpropagate through the whole simulations without problem. So what we propose here is a model that we would like something that is more like the thing you see on the left, that is loosely based, at least in the beginning, on some of the principles that people know drive real morphogenesis. And most prominently biochemistry and mechanics. We will not deal with geometry in this specific case, meaning not spatial constraints in the model. So let's say the very simplified model that we propose here to try and play with, that is, let's say, complex enough to see what comes out of it, is actually that of a cell that secretes some chemical signals that diffuse in space and adheres to other cells with a specific potential and receives as a feedback mechanical stress. And of course, based on the inputs that the local cues that the cell receives, the cell will compute probability of dividing. I will go a bit more into detail in the next slides. And so this is the way we model mechanical potentials. This has been shown to be very recently, actually, to be a pretty good description of what happens in experimental data, which is to model the cell interactions with a potential that is repulsive at short distances and attractive over longer ones, meaning that if you're very close to one another, one cell to another, like the last line of the figure on the right, then you repel your neighbor. But if you're a bit further away, you attract it, meaning that you're secreting let's say, whatever they are, E-caderins or whatever your favorite adhesion molecule is. And then we have to have diffusion. We know that chemicals, morphogens, essentially, play a big role in this kind of processes. So we want, and this is like a constraint on your system. Like the fact is that you cannot really choose whatever function you want to optimize in general, as you would do in a general machine learning context. You cannot choose whatever function is most comfortable with you to take gradient of. And you have to choose a function that is physically meaningful. And so in this case, like all of these building blocks are basically thought to be swapped out at some point where more and more realistic and physical description of the system. So for the moment, we just model diffusion with the steady state diffusion and degradation, meaning that we have these exponential profiles of chemical concentration in space, and also cells are kind of known to be able to sense chemical gradients, and especially so in tissues where they can actually communicate. This has been shown in this paper that cells communicate through gap junctions at a distance that is variable. The authors claim between 2 and 3, let's say, cell distance, let's say. We just to be sure, we just limit ourselves to a communication between first neighbors. So the cells will communicate to their neighbors what their own chemical reading of the environment is, and the cell will receive these signals as input and compute an approximate and local noisy estimate of these gradients. Now, the main thing, of course, is how do cells take decision, and also here we kind of decided to stick with for the moment with the simplest machinery that we have. Of course, what is inside the cell is very different from a neural network, which is what we're using here. And again, this is a building block that can be swapped out and substituted with more, let's say, physical models, that is gene regulatory network or whatever, OD models, Gillespie simulation, whatever you would like to have, depending on what kind of regulatory mechanism you are dealing with. But the main properties of this setting is that there are some inputs that the cell receives locally. Those inputs gets mapped into a hidden state. Now, it doesn't just get mapped into a, let's say, hidden cellular state. But we wanted also to add memory because, of course, cells do have some sort of memory of their past state. So what we are outputting, and this is very similar in spirit to the neurocellular automata, I think, we are outputting a delta state, so an update for the state. And this will basically give you a dynamical system where the cell state is updated at every step. And then we take this hidden state, and we suppose that it contains all of the information there is to know for the cell about its environment. And we use this hidden state with like some simple, let's say, linear, or let's say at least one layer networks afterwards to decide how much you should secrete. Like the functional form of this thing is, again, pretty arbitrary, but it makes kind of sense. What should your, let's say, division probability be, and other possible choices that the cell can make. So this is the overall setting. And the overall setting is, of course, that you have some parameters for all of these building blocks, like the potential, the diffusion, you have the diffusion coefficient, you have the coefficients of the potential, you have a bunch of parameters, and each of the building blocks in the simulation have a bunch of them. And the idea is that depending on which problem you're actually dealing with, you would be able to choose which of these parameters you want to optimize over, like depending maybe on your data measurements or your particular engineering problem at hand. And so what happens in a single step of the simulation is the thing that you see on the left. So every, let's say, every kind of sky blue building block there at t equals 0, t equal 1, it's just another iteration of this whole state update. And the problem with this is, again, that the black arrows between one update and the other imply cell division. Cell division is a discrete action, and therefore it is not possible, let's say, in an obvious way to take gradients in between those steps. So what we resorted to is basically, again, the most simple thing you can do that surprisingly already works pretty well, even though it's probably, let's say, theoretically slightly wrong in a number of ways, is to use policy gradients. That is, at each time step, the system, we take the system as input, we measure some property that we want to optimize for in that step, and then we take the gradient of the log probability of the division that we had. Now, this is like, I will not go into details too much about this because it would take too long, but this is a well-established procedure in reinforcement learning. Okay, so running forest simulations, this is what we get if we start off from a state where basically the last layer of the updates that you've seen before is just 0. So every cell has the same probability of dividing. You see that you get basically cell divisions randomly here and there, and the final blob is something that is sort of isotropic. Now, depending on how many cells you simulate, it is more or less approximating a circle because you have finite size effects coming into play, of course. And also, like, for example, here, if you have 3 chemicals diffusing, you see that the chemical distribution is actually not really interesting in any way, right? So what we would like to do now is a very simple, let's say, proof of principle thing. So suppose that we now have a system with 2 chemicals just diffusing, and we would like this system not to grow in a circular shape, but in an elongated shape. So that the loss function is actually just the sum of the squares over let's say, of the y positions of the cells. And we can actually do that in a reasonable way, depending on how many parameters we choose for the network, how many chemicals, we can get more or less elongated shapes. If you want to really push this thing to the limit, you get like a very spaghetti-like thing. But here you see that the cell cluster is now not dividing randomly anymore. And the more you go on, the more you see that the shape is not a circular one anymore. And in fact, when you look at the final state, what you see is that the picture on the left shows you the probability of division. And what the system has learned is that if you divide in the middle of the cluster, then you have more possibility of being pushed out on the sides and therefore creating an elongated shape. The funny thing is that if you do this has nothing to do, like the loss itself has nothing to do with the chemical distribution in the system in any way. But it turns out that in order to do this, the system kind of learns or discovers that a very efficient way of doing this with chemical regulation is to have two different and opposing chemical gradients along the y-axis. So where you have one chemical that is secreted only on one side that blocks division on one side and the other that blocks division on the other side, so that you have only division in the middle. And this is totally emergent. We never ask for any property of the chemical gradients themselves, which is kind of interesting. Now, a more complex task, but that is also pretty relevant, is that of branching, right? Branching processes are very present in morphogenesis, and we would like to see whether our system can also deal with these kind of things. So now here, it's the loss function itself is not easy to define anymore. What is a loss function for branching? So again, following the line of least resistance, we just came out with this sort of masking reward function that we give to our system. So at each time step, you add a new cell, and then you see whether your cell is within the green area on the top left. You give a bonus to the system. And if it's outside of that, you give, let's say, kind of kick to the system to say that it's going in the wrong direction. Again, sorry, I probably forgot to mention this, but it's easier to see why this is reasonable if you go here and see that this factor, this loss, this reward, this advantage function, whatever it is that you're calculating that multiplies the gradient of the probability is a sort of, let's say, not really the reward itself, but something very similar. And what happens here is that if you get a positive reward, you will push towards having higher probability for the same action at the next run because it was a good one. If you have a bad reward, you will basically go against the gradient and diminish the probability of the same function at the same run, at the next run. So what you're actually, let's say, trying to do is to maximize the probability of the whole trajectory given choices that you made, that a good trajectory, that you get a good trajectory given the choices that you made in the past. And as you can see, this can actually happen, which is pretty amazing, I think. And on the bottom line, you just see that also here you have some sort of, say, chemical distribution, even though it's not an obvious one. But this is just to say that this can be done in principle. And the last, well, this is just another test, like, again, of course, inspired by the fact that stuff can regenerate. And here you see that once you get that structure, you can kill a lot of cells after you produce that. And this is again, not being trained for. So you just use the optimized parameters to grow, then you kill a lot of cells at the end of the simulation. On the left, it was like 60% kill. And you see that the cells grow back. There are some errors, but you're still like not too far away from what you would like to have. And if you like try to sweep and kill a bunch of them, you see that, of course, the precision of the reconstruction goes down the more cells you kill, because like the resulting cells will be everywhere, essentially, you know, not always starting from the same point. But still, the system seems to be pretty resilient to these kind of things. So this is the very last thing I will show you. Yeah, I'm very sorry for that. And this goes a bit more in the direction of dealing with real systems. This is work that was done by Ramya Deshpande. And this is another toy problem that is closer to an experimental system. You have a concentration of chemical gradients that is radially distributed. You have a lot of morphogen in the middle of the cluster, a lot less on the border. So the cells grow more let's say, in the middle of the cluster. And this, of course, builds up stress because cells divide all together and they have no time to grow in the middle and relax this compression that is formed by the high division rates. And well, you see that if you have the unoptimized version, this is actually, sorry, this is the wrong GIF, actually, I think. Yeah, this is, they're actually swapped. I'm very sorry for that. So this is the unoptimized version where you have high division rates in the middle, and you see that a lot of division are happening in the middle on the left, and those were swapped. You see that the cell divisions are kind of spread more around, and as a nice side effect, what you see is that if you have, this is the right one, if you have a loss of cell division in the middle, this is the stress that builds up in the middle, the mechanical stress, the compression. While in the optimized version, what you see is that the stress builds up a bit when the division is done, but then it gets dissipated very fast. And this was achieved by asking that the system be dividing at a constant rate, essentially. And there's a nice bonus to this, and this is the very last thing, I promise. We can compare essentially the stress division curve that we get by imposing this very simple task on the system with something that is, again, sort of, this is not really an experimental result, but it's a guess made in a paper coming from experimental results of the same curve, and we don't actually have, let's say, elongation stress, we only have compressive stress, and you see that the curve kind of resembles the thing on the right, which is kind of promising. And this very last thing, I would like to spend my very last seconds remembering very dear friend and colleague, Alma that had a huge role in developing this at the beginning of this project, and that she very sadly passed away some time ago. And she was my supervisor in Lausanne, and a brilliant person and a brilliant scientist. And I mean, she made us all very proud of having known her. And of course, my thanks also to Ramya and Michael that collaborated with us and that were super supportive. Thanks.